Hello everyone, this is Aishwarya, currently studying in Sri Venkateshwara College of Engineering. Today's topic is about bubble sort with time efficiency. Introduction to bubble sort. Bubble sort is a simple sorting algorithm that repeatedly steps through a list, compares adjacent elements, and swaps them if they are in the wrong order. The algorithm gets its name from the way smaller elements bubble to the top of the list. This means it compares the adjacent elements, and if it is the elements are in the wrong order, it swaps them. This is called as a bubble sort. How bubble sort works? It works on three steps. It compares, swaps, and repeats. Compare the first two elements in the list, and swap is about if the element is out of the order and it swap them. Repeat. Move to the next pair of elements and repeat the elements swap process. Time complexity of bubble sort. There are three time complexity of bubble sort. They are the best case, worst case, and the average case. Best case is written as O of n. When the list is already sorted, bubble sort only needs to go through the list once, taking linear time. This means the best case only takes the linear time. It can be written as O of n. Worst case, it can be written as O of n square. When the list is in reverse order, bubble sort must perform n-1 passes, each with n-1 comparisons, resulting in the quadratic time complexity. And this means it needs a quadratic time complexity. Average case, it can be written as O of n square. On average, bubble sort as a time complexity of O of n square must be the efficiency of large datasets. Average case contains only the efficient of large datasets, and the worst case and the average case can be written as O of n power 2. Best case scenarios. There are sorted list, no swaps, efficient. Sorted list means in the best case scenario, the list is already sorted and the bubble sort only needs to go through the list once, taking linear time. No swaps. Since the list is already in order, no swaps are necessary and the algorithm can terminate early. If the list is ready in its order, there will be no swaps are necessary and it terminates early. Efficient. The best case time complexity of O of n makes bubble sort efficient for already sorted list. For the sorted list, the best case complexity of n can take the efficiency. Worst case scenarios. Worst case scenarios. Reversed list, maximum swaps and quadratic time. In the reversed list of worst case scenarios, the list is in reverse order and the bubble sort must perform n-1 passes, each with n-1 comparisons. That means if the list is in the reverse order, the worst case scenario takes place. Maximum swaps. Since the list is in reverse order, the algorithm must perform the maximum number of swaps to sort of the list. That is, if the swaps of the sorted list are more, then it is in the reverse order, then the maximum swaps takes place. Quadratic time. The worst case time complexity of O of n square makes bubble sort inefficient for large and the reversed lists. Average case scenarios. There are three types of average case scenarios. There are three types of average case scenarios. They are the random order, quadratic time, and need for optimization. Average case of random order specifies that in average case, the list is in random order, requiring a mix of comparisons and swaps. That is, it requires a mixture of the comparisons and swaps to list the random order. Quadratic time. The average case time complexity of O of n square is the same as the worst case, making bubble sort less efficient for large databases. If the set is in the large databases, it makes the bubble sort less efficient and it is same as the worst case. Like the quadratic time is same as the worst case. Need for optimization. To improve the efficiency of bubble sort, optimization such as early termination can be implemented. For the optimization, early termination that is can be implemented for the need of the optimization. Optimizing bubble sort. There are three types in this. There are the flag, reduced passes, and improved efficiency. Flag is the introduced to flag to track if any swaps occur during the current pass. If no swaps, the list is sorted and the algorithm can terminate easily. If there are no swaps in the bubble sort, then the list is sorted particularly and the algorithm can be terminated early as possible. Reduce passes. Keep track of the last swap position on the next pass. Only compare elements up to the last swap position, as the rest of the list is already sorted. Improved efficiency. This optimization can significantly improve the time complexity of bubble sort, especially for nearly sorted lists. These are the flag, reduced passes, and improved efficiency are helpful for the optimizing of the bubble sort. Conclusion and recap. Time complexity, strengths, weaknesses, optimizations of the bubble sort. Time complexity of bubble sort are best case, worst case, and average case. Best case can be written as O of n, worst case can be written as O of n power 2, average case can be written as O of n power 2. That is, the worst case and average case can be written as O of n power 2. Strengths of bubble sort. Simple to understand and implement, efficient for small, already sorted lists. Weaknesses of bubble sort. Inefficient for large, unsorted data sets, quadratic time complexity in the average and worst cases. Optimizations. Early termination, reducing number of elements, tracking last swap position.